All right, let's go back to this problem right here. This is the one from the last video. You can see that the values for the batteries are the same, the resistances are the same, and these were the answers for I1, I2, and I3. I want to use this problem to address another question, and that is, how do you determine the potential difference between 2 points in a circuit? Let's say you took the ends of a voltmeter and you put them right here, from that top node to this bottom node here. Or you put them across this resistor here, or maybe you went from there down to this corner here. How do you determine the potential difference between any 2 points in a circuit? Well, let's begin with the easy case. Let's say that the 2 points are right here. Those 2 points are connected together. Electrically speaking, those are the same point. So there is zero potential difference between those 2 points right there. And if you were to need to determine the potential difference across that resistor, let's say, what's the voltage across that resistor? Well, the voltage across that resistor, V, is just going to be I1 times R1. In other words, you just use Ohm's law over that single element. And the same would be true down here. Over here it would be I3 and R1, I3 and R1 down here as well. Here, I2 and R2. And let's say you wanted to determine the potential difference across this battery. Well, it's just going to be whatever the voltage of the battery is, which is going to be 2.1 volts. Okay, so the real problem then is not an individual element, but when you have multiple elements, let's say between this top node and this bottom node, how do you determine that? Well, it's pretty straightforward. There's a pretty easy rule. Let's label this top node A and this bottom node B, like that. And let's say we want to know the potential difference between A and B. We would write that this way. V sub A minus V sub B is what? What's the potential difference? Well, the rule is this. To find the potential difference between any 2 points in a circuit, you start at one point and you traverse the circuit to the second point, and you follow any path. Any path could be over here to the left or down the center, over here to the right. Absolutely any path that the circuit allows. And then you add algebraically the changes in potential. So if it's a potential drop or a potential rise, you either add or subtract those. Let me show you what I mean. Let's say we're after the potential between A and B. You start at this point and go to this point, following any path. So let's start at A and go to B, and let's go right down the middle here. So we'll write it this way, V sub A. That's the potential where we're starting right here. And then we cross over R2, and since we're going in the direction of the current, that's a drop, so let's call that negative I2 R2. And then we're going across E2 here, and that's going from the high side to the low side. So that's also a drop, minus E2. And then we end up at point B. So that is equal to the potential at B. So we just wrote an equation. Now solve the equation so that V sub A minus V sub B, and you put all this stuff on the right hand side, is I2 R2 plus E2. So whatever that turns out to be there, then that's the potential between A and B. So what is that? Let's see, I2 is negative 0.40 amps times R2, which is 3.5 ohms, plus E2, which is 6.3 volts. You add all of that up and you get 4.9 volts. So there's the potential between A and B. Now let's do the same thing, except let's follow a different path, let's say. Let's go from A to B around this part over here on the left. All right, you follow the same procedure. You start at A, V sub A, and then we're going to minus I1 R1 because it's a drop. We're going the direction of the current there. and then minus E1, and then we're still going in the direction of the current, minus I1 R1, and now we're at B, equals V sub B. So let's solve for VA minus VB, and that's going to be I, now which I was at? That was I1. I1 R1 plus E1, and there's two of those, so I could just stick a 2 in front of that. Okay, let's plug in the numbers. 2 times I1 is 0.82 amps, times R1, R1 is 1.7 ohms, plus E1, 2.1 volts. Add all of that up, and what do you end up with? 4.9 volts. Same. And it would be true if we went over here towards the right-hand side as well. So, to find the potential between any 2 points in a circuit, you start at the first point, write down the potential at that point, and then follow whether it's rises or drops to the second point, and the potential is equal to that potential at the second point. Then you can solve for whether or not you want VA minus VB. We could have equally written VB minus VA, and they would have been exactly the same, except they would have one of them would have been negative. Okay, so you can see how that works there. You can find the potential between any 2 points using that technique. Okay, let's talk now about RC circuits. RC circuits are circuits that have both a resistor and a capacitor in them. Now, unlike the resistor or capacitor circuits that we've talked about, RC circuits are going to be transient in nature. That means that they're going to do something over a short period of time, and then they're done doing that. That means it's going to be some function of time, and we need to start thinking in terms of what happens over a potentially brief period of time. It could be several seconds, but it could be milli or microseconds as well. Now, the way we're going to set this up is we're going to build a circuit here that has the ability to charge a capacitor. And then we're going to take that charged capacitor and we're going to put it into a circuit with a resistor. So here's my capacitor. It has a capacitance of C. Now there's a voltage source over here. Let's just say V0 is that voltage right there. And there's a switch here, and this switch has two positions. It has an A position and a B position, and it's able to flip back and forth between those two positions there. Now let's hook up a resistor over here. And there's my resistor. Now, when the switch is over fully in the A position, when it's touching the A, then the right-hand portion of this circuit might as well not even be there. In fact, when it's in the A position, this is just a battery hooked up to a capacitor, and it's charging up a capacitor. So there's the capacitor, and there's that. So it's going to create a current that's going to go over here, and it's going to build up a positive charge on one plate, a negative charge on another plate. And it's going to do that fairly quickly. We're not interested at this point in how quickly or what that looks like. We just want to charge the capacitor. And when it's over in the A position, let's say it's been there long enough for this capacitor to become fully charged, then we flip it over into the B position. And let's say we do that at t equals 0. So we've set our stopwatch at t equals 0, and we flip that exactly at t equals 0 point. Okay, well, when we do that, this capacitor has some charge already on it. Now, how much charge does it have? Well, whatever charge was built up when it was back in the A position. And you can figure that out using the capacitor equation. Q, let's call it Q0, that's the initial charge that's on the capacitor at t equals 0, is equal to C times V0. You know that right at t equals 0, when you flip this thing over, it's going to have a potential equal to that of the battery. And that's the V0. So the charge on it is going to be Q0, which is given by this equation here. All right, now when it's over, this is when it was in the A position. Now it's in the B position. The charged capacitor is here, and this is essentially a resistor and capacitor circuit. So there's a capacitor, there's a resistor. This is an RC circuit. So at the moment the switch is flipped, a current begins to flow. Let's call that current I right there. All right. Now, KVL should apply in this case as well as any other case. And both of these are passive elements. And as long as we are traversing in the direction of the current then all the way around this, we should see a drop across this resistor and a drop across that resistor. So we've got two drops, and that should equal to the rises, which are none in this case, so it's 0. So let's say the first drop is minus I times R, so I'm using negative signs for drops. And then the next drop is this here, so we have a voltage drop across the capacitor. But remember, based upon the capacitance equation, the voltage drop across the capacitor is going to be the charge that's on the capacitor divided by C. Now, what you see here, this is only the initial charge. You can imagine what's going to happen here. When the switch is thrown, that current begins to flow, and at that point we have energy that's being dissipated in the form of heat through the resistor. So the current through the resistor generates heat, and we have energy dissipated away at a rate of I squared R. That's the power. All right, so this is a drop. This is a drop. This Q is not that Q. That's the initial Q at t equals 0 right there. So this Q right here is going to change with time. The current's also going to change with time. But both of these drops, that's on the left-hand side of the equal sign here, that's the sum of the drops. Well, where are the rises? There aren't any. So it's got to be 0. So this is an equation then that describes this circuit. Now, let's rewrite the terms. We can divide by -1 and get rid of the negative signs. So we got IR plus Q over C equals 0. Now I'm going to make a substitution here. You know that from the definition of current that I is equal to dQ dt. So let's take that substituted in here, and I have R times dQ dt plus Q over C equals 0. Now I'm going to write this in what's called standard form. Standard form for this type of equation. This is a differential equation. You get rid of the coefficient in front of the first order term just by dividing both sides by R, plus 1 over RC times Q equals 0. Now, this is a differential equation. If you haven't had the differential equations class, don't worry. Don't worry. I'll show you how to solve this one. This one's probably one of the easiest type of differential equations to solve right here. And you'll see, if you've had calculus, you'll see it's pretty straightforward. But I want you to think about what this equation is. This is called an equation of state. And what it's describing here is the discharging behavior of the capacitor. The solution for this is going to be some Q that is a function of time. Now, there's going to be a function over here on the right-hand side that's going to have a t in it somewhere. So that's what I mean. Q is a function of time. Because you expect the charge, Q is the charge across the capacitor, you expect that to change over time as the energy is being dissipated away through the resistor. And that's what we will discover here. When we solve this, we will get this function here. This is discharging, what I'll call discharging behavior. The discharging behavior, or the discharging equation here. Now, I'll tell you what the solution is right now, and then I'll show you how to get it. The solution looks like this. It is Q naught times E, that's exponential E, to the negative T over RC. That's a decaying exponential. So if you were to graph Q versus time, this is Q as a function of time versus time, what you would discover is at t equals 0, when t equals 0 here, this term becomes 0, so we've got e to the 0. Anything raised to the 0 power is 1, so that becomes 1. So at t equals 0, Q is just Q naught. So let's say that right there represents the value Q naught. Then as time goes by, this thing decays. This is the nature of a decaying exponential. It decays down like this, and over time it reaches 0 in the limit. Okay, so it falls off as the decaying exponential here. This Q naught is the maximum value that it will have, and this RC here, that RC is called a time constant. And that time constant determines how quickly this thing does whatever it's going to do. So in this case, it's falling off. The charge is falling off, so it determines how quickly it falls off, or how slowly it falls off, depending upon its value. All right, now all of that was just kind of thrown at you. That is the solution. This is not a math class, it's a physics class. We care less about how to go from this step to that step. We care less about that in a physics class than we do about your understanding of how that solution came about and how this equation right here is describing the discharging behavior of the capacitor. How did that solution come about? I'll show you now. Let's go rewrite the equation itself. dq dt plus 1 over RC Q equals 0. Well, how do you solve this? This is a first order ordinary homogeneous differential equation. First order means that it has a first order derivative, so there's not a second derivative, there's only a first derivative here. It is ordinary because it has regular derivatives and not partial derivatives here. And it is homogeneous, which is just a fancy way to say it's equal to 0. So this differential equation right here is first order ordinary homogeneous differential equation. And the way you solve it is through a technique called separation of variables. Now, separation of variables just means you get all of the variables of one on one side and all the variables of the other on the other side. Well, what are the variables here? The variables that you want to solve for is Q. So there's a Q there and there's a Q here. But time is also something that's going to change, so T is also considered a variable. So what we need to do is get all the Q's on one side and all the T's on the other side. The 1 over RC, that's a constant. You know, unless you're physically changing your circuit, the 1 over RC is not going to change for any specific circuit. Okay, so let's do this. dq over dt. What we'll do is we'll put this minus 1 over RCQ on the other side. And now to get the Q over here, let's divide both sides by Q. And to get the dt over here, let's multiply both sides by dt. And you can see what's going to happen here. The dt's cancel, so you've got dq over q. And over here on this side, you got 1 over rc dt. All right, we've separated the variables at this point. Now we've still got these these derivative things here that we need to get rid of because we want, remember what the solution looks like. The solution looks like this. It's got none of those derivatives in it, none of those differentials in it. So how do you get rid of that? Well, you integrate both sides. So let's integrate this side. We'll also integrate this side. Now, the limits of the integration are kind of important here. We're going to go from whatever the initial value of charge was, we've called that Q naught, to the charge at some time later, which is T. So this is really the charge at T equals 0. And this is the charge at time T later, arbitrary time T. Now, since we're doing that, the initial time here is going to be, we could call that T naught. Now, it may be that T naught is 0. And then this is some arbitrary time later T. Okay, let's do the derivatives now. Well, this is dq over q. That's going to be a natural log of q. And we evaluate that from q naught to q t. And that's equal to minus 1 over rc. And when we do this derivative, that's just going to be t minus t naught. Okay, let's plug in our limits here. I've got natural log q of t minus the natural log Q naught. Okay, this is a difference in natural logs. You may recall that you can make this a ratio, so we could write this as natural log Q of t over Q naught is equal to all of this stuff on the right-hand side, which is, let's go ahead and write it down, minus 1 over RC t minus t naught. All right, now we've got this natural log. We need to get rid of that. So how do you get rid of that? Well, you take the exponential of both sides. And when you take the exponential of both sides, you've got Q of t over Q naught on the left-hand side. That's Q naught. And then on the right-hand side, you take the exponential of all that, and you end up with e to the negative, let's just say t minus t naught over RC. All right, let's multiply through by Q naught to get the Q of t on one side by itself. And what do you end up with? Q of t is equal to Q naught e to the negative t minus t naught over RC, which looks an awful lot like this. The difference is we've just got t on top instead of t minus t naught. Well, remember, I said this could potentially be 0, and in our example here, let's go back here. In our example here, we chose to flip the switch at t equals 0. So our t naught, the initial time, is 0. So you plug in 0 right there, and you're finally left with Q of t is equal to Q naught e to the negative t over RC, like that. Now, oftentimes what you'll see is this RC right here is a time constant. It is abbreviated as a small Greek letter tau, and that is RC. So you'll see this written as Q of t is equal to Q naught e to the negative t over tau, like that. So there we've got our equation for Q, and that is how we jumped from this step down to that step there. All right, well, then a few interesting things that we can come up with from that. First of all, remember our circuit looks like this up here, and when we flip the switch over at t equals 0, current begins to flow. I should be pointing at this circuit here, this one right here. The current begins to flow, and over time the charge here decays because of the solution. Q of t equals Q naught e to the negative t over tau. The tau is RC that determines how quickly it decays. All right, so after a long period of time, meaning when t goes to infinity, the exponential becomes 0 here, so the charge is 0 across the capacitor. All right, a good question might be, well, what's the current? What is the current? Well, remember what current is. It's given by this here. So I've got Q. If I take the derivative of this with respect to time, I will have the equation for the current. So I equals dq dt. It's going to be the derivative of this. Well, Q naught is a constant, times the derivative of this with respect to t, but that's an exponential, so the derivative is just going to be the exponential itself. Now multiply by the derivative of what's up here. So the derivative of that's going to be minus 1 over tau, in parentheses. That Q naught goes over there. All right, so what is that? That's negative Q naught over RC e to the negative t over tau. So this is the current, and you can see that that's going to be a function of time as well. All right, what does that look like? Well, it looks the same as this over here. Of course, the maximum is different, but it decays at the same rate here. Both of these are decaying exponential. Now let's discuss this negative sign out front here. What does a negative sign indicate when we're talking about, currents? When we're talking about currents, what that means is direction. So the direction is going to be different than what we talked about here. But the direction of the current here is kind of less important to us than the equation itself here. All right, the equation is going to look the same. So if we have the I versus t, the maximum value up here is going to be Q naught over RC. And then over time, it's going to decay and reach 0 in the limit because it's a decaying exponential. Now, if we did the same thing for Q versus time, you know that this is Q naught. That's the maximum value. And it decays as well. All right, now we've called that tau. We've called it a time constant. Let's investigate that a little bit more. One of the interesting things, if you take R and C and multiply them together, the units for those turn out to be a unit of time. So R times C is actually time. You can tell that here because T on top is time, the bottom is also time. That means there's no unit associated with the exponential here. The exponential is the time varying portion of this function, whereas what's out front is the coefficient that tells you what the maximum value is. And that's true in both of these cases. Coefficient tells you the maximum value. But let's look at the unit here. First of all, R. You know that R is V over I. That's voltage divided by current. This is what we called Ohm's law. You also know that C, come from the capacitor equation, is going to be Q over V. So let's take these two things, multiply them together. Then RC is going to be V over I times Q over V. And what are we left with? Q over I. Now, let's look at the units for this. Unit for Q is Coulomb, divided by the unit for current, which is ampere. So a Coulomb per ampere. But what was that? Coulomb, an ampere is a Coulomb per second. So what happens? The Coulombs cancel, and we're left with 1 over seconds, which is just seconds. So this does turn out to be a unit of time here. It controls how rapidly the decay occurs. But it's kind of unusual for people to think about tau, RC, as being a time element. So let's build a little chart here. Let's say we put time in this column and we put e to the negative t over tau in this column. Well, let's let 1 tau of time transpire. If you let 1 tau of time, then t is now 1 tau, so we've got e to the negative 1 tau over tau, which is just e to the negative 1. And that's something you can plug into your calculator, and it turns out to be about 0.37. So what does that mean? That means after 1 tau of time, remember the equation that we're looking at is Q equals Q naught e to the negative t over tau. That means after 1 tau of time, this exponential is now 0.37. So Q is 0.37 of its maximum value. So it's 37% of its maximum value after 1 tau of time. Okay, let's continue this, and let's say 2 tau of time. Well, that's going to be e to the negative 2, and that turns out to be 0.14. So after 2 tau of time, Q is 14% of what it was originally. After 3 tau of time, e to the negative 3 is 0.05. So now we're down to 5% of its original value after 3 tau of time. What about 4 tau? 4 tau, e to the negative 4, turns out to be 0.02. So we're down to 2%. 5 tau, e to the negative 5, 0.01. So after 5 tau, we're less than 1% left. So you could carry this on forever. 6 tau, e to the negative 6 is 0.002. So after 5 tau of time, we are 99% finished. We're less than 1% of the initial value. So if you think about this equation right here, remember I said if we graphed it, Q versus time, it starts at its maximum value of Q naught, and it decays over time, but where does it actually reach 0 here? And the answer is in the limit. As t approaches infinity, Q approaches 0. So from an engineering perspective, or even physics perspective, whatever, it never truly goes to 0. So that leads us to this. After 5 tau of time, it is effectively finished. In other words, when it's less than 1% left, when it's 99.9% done, then in that case, we are saying that it's 0. So a good question would be, how long does it take this to decay? How long does it take the charge to decay? The answer is 5 tau. 5 tau is how long it takes the circuit to do whatever the circuit is going to do. 5 tau of time. And that would be true if we're talking about charge. It would also be true if we're talking about current, because remember, that's some maximum current, e to the negative t over tau. It would be true of voltage. If we looked at the voltage across the resistor, it's going to be some maximum voltage times e to the negative t over tau. What if we looked at the voltage across the capacitor? The voltage across the capacitor is just going to be Q over C. And what does that turn out to be? Well, this is Q. It's going to be some maximum voltage, e to the negative t over tau as well. So everything decays at the same rate here. It's going to be 5 tau. You might say, well, where did this one come from? Well, remember, IR is the voltage across the resistor, and this is I. So plug in I there, and you're going to end up with some maximum voltage, and it's going to decay over time. So once again, everything decays at the same rate. And how long does it take it to complete whatever it's going to do? The answer, 5 tau of time. All right. What we've done so far is we've looked at discharging behavior. Let's go on now, and let's look at how charging behavior works for an RC circuit. For charging behavior, let's set it up this way. Let's say that we have a battery, and we'll put a switch here in the circuit. Here's the resistor, and here's the capacitor. The switch is open before t equals 0. The switch is closed at t equals 0. Now, before t equals 0, there is no charge on the capacitor, so this is a completely different situation than we had before. There's no initial charge on the capacitor, and there's no current flowing before t equals 0, but after t equals 0, this switch is closed and a current begins. Now, as you can figure out, this capacitor is going to charge up, and once it's fully charged, the current stops. Remember, the capacitor is going to reach a final potential difference across its plates that's equal to the potential of the battery. So if I were to, you can almost guess what's going to happen here. If I say this is the voltage across the capacitor over time, well, what happens right at t equals 0? There is no voltage across the capacitor. It's empty. So it starts down here. But after a long time, the voltage across the capacitor is going to be E, whatever that value is. All right, so that means that somewhere out here at some time later, this thing has risen up somehow. Maybe it's gone like that, maybe it's gone like that, maybe it's a straight line. How did it get there? Well, I'll give away the answer. It approaches it like this and reaches the maximum in the limit. So this is not a decaying exponential, this is a rising and leveling off exponential. So you know what the answer looks like, at least graphically, but just by using your circuits knowledge, you figured that out. You could also figure this out. What about the current versus time? Well, at t equals 0, before t equals 0, there was no current, but right at t equals 0, the current instantly jumps up to its maximum value. And then as time goes by, so you expect this to be decaying exponential, like that. All right, what about, let's say, the voltage across the resistor versus time? Well, the voltage across the resistor, you got to think about what causes the voltage across the resistor. The thing that causes there to be a voltage across the resistor is the current. And if the current does this, then what do you expect the voltage to do? Well, I expect it to start out high. Its maximum value is going to be E. And over time, it's going to decay to nothing. Now, how long does it take it to decay? 5 tau. How long did it take this to decay? 5 tau. But what about this? See, it rises up to its maximum value. How long does it take that to do? The answer is 5 tau of time. But what is tau in this case? Is tau the same thing as it was before? All right, we'll figure that out. And in order to figure that out, we need to write another differential equation. Now, I understand this is not a differential equations class. I will write the differential equation for this one, and I will give you the solution. Because remember, the solution is more important than your ability to derive a solution from an equation. All right, so let's get started here. What we want to do is we want to start and write a loop equation, just like we did before. Okay, we're going to go in the direction of the current here, so we pass through the resistor. The voltage drop is minus I times R. Then we pass through the capacitor. What's the voltage across it? It's a drop. It's Q over C. Then we pass through the battery. It's a rise, so it's going to be plus E equals 0. All right, let's rearrange the terms here. I've got I, R plus Q over C is equal to E. So I just changed sides to get rid of the negative sign here. And now we'll make the substitution that we did before, that I is dQ dt, and we'll write this as R dQ dt plus Q over C equals E. There. Let's write it in standard form. dQ dt plus 1 over RC times Q is equal to E over R. Okay, what is E over R? E over R is I. Okay. All right, now, our job at this point is to find the solution, and rather than go through the steps like we did previously, I will just jump to the solution here and tell you that Q, as a function of time, is equal to C times E times 1 minus E to the negative T over RC. Once again, you see that we have tau, the time constant, equal to RC. Now specifically, this is called a capacitive time constant because we got a capacitor in the circuit here. Later on, you will encounter an inductive time constant, and it'll be different. It won't be exactly this same. Okay, but right now, the time constant is RC. All right, there we've got the equation for the charge as a function of time. Now, what does that look like? Well, at t equals 0, it's going to be e to the 0, so this term is going to be, what, 1. And we have 1 minus 1, so it gives us 0. Now, this is voltage across the capacitor, but the charge across the capacitor versus time is going to look the same way. It's going to start down here, and then after a long period of time, let's say as t goes to infinity, well, what happens to this? The exponential, as t gets very, very large, this is e to the negative t over tau, so this becomes very small, and in the limit, it goes to 0. So in the limit then, q of t is just c times e, so the max value is going to be c times e. So that's the max at which it levels off, and it approaches and levels off like that. Okay, so that's the charge across the capacitor. What about the current? Now there's only one current here, so the current through the capacitor is going to be the same as the current through the resistor. So you can figure that out using this relationship here. You take the derivative of this with respect to time. Okay, well let's see what happens when we do that. This CE times 1 is, that's a constant, so the derivative of that's easy, that's 0. So I've got this CE, I've got this minus CE times the derivative of this, which is e to the negative t over rc, times the derivative of that, which is going to be minus 1 over rc. So the negatives will cancel each other, the c's will cancel each other, and what have I got? I've got e over r, e to the negative t over rc. Or, let's write it a little differently. Let's write it down here. I of t is equal to some maximum value. That's the initial value times e to the negative t over tau. So what does that look like? Well, it looks like this. This is the maximum value, and that turns out to be just e over r. That's from Ohm's law. I equals v, which is e over r. So that's the maximum value. It's what happens right at t equals 0, switch is closed, and instantaneously we have a maximum current, and then it slowly decays. Okay, so we've found charge, we found, putting a square around the wrong thing there. We found an equation for charge, we found an equation for current. What if I want to know the voltage across the capacitor? Voltage across the capacitor is Q over C. Well, Q changes with time, so you take this right here and you plug it in, and you'll notice the C's are going to cancel, and I'm left with E times 1 minus e to the negative t over tau. So what does that look like? That's going to look like this. It's going to level off at a maximum value of E. So this is V voltage max for the capacitor. And what's happening is, as the current flows around here, the voltage across the capacitor is charging up, and it charges up in such a way that it looks like this. And it reaches its maximum value of E. And that's what this equation shows. Okay, well, what about voltage across the resistor? Voltage across the resistor is just I times R. Well, what's I? I is this right here. Okay, so take this, plug it in here for I, multiply by R. You'll see the R's will cancel here. And what am I left with? E times e to the negative t over tau. So while the voltage of the capacitor is rising up and building like that, the voltage across the resistor is decaying. So that if we were to graph both of those, let's just use this right here because we've already got the voltage of the capacitor graphed here. If I also now graph the voltage of the resistor, it starts off up here and then decays down to nothing like that. So as the voltage across the capacitor rises, the voltage across the resistor decays. So this is the V sub R curve, and this is the V sub C curve. Okay, so you can see what's going on there. By the way, it may not be too obvious for my drawing here, but if you were to take at any specific time, add up that value of V sub C and this value of V sub R, add them together, and it would be the maximum value. Now, how does that work? Well, V sub R plus V sub C, let's see, that's just going to be E times e to the negative t over tau plus E times 1 minus e to the negative t over tau. And you'll distribute that E, and you'll see that this term and that term cancel each other, so what's left? E. So the sum of these two voltages is equal to E for every time t. Now what does that mean? That means what you already know. The voltage across this plus the voltage across that has to equal the voltage of the battery. In other words, these two elements are in series with each other, so their voltages add to be this. So regardless of what time we're talking about, regardless of what t is, the two voltages sum up to be the voltage of the battery for all time. Okay, let's take what we've learned now and see if we can solve a problem or two. Let me sort of sum things up though on the back side here. There have been really only two general forms of equation that you've seen. x equals x max times e to the negative t over tau. That's the decaying exponential that starts off at some x max value, goes and decays over time. You've seen that. You saw that. The other form of the equation we've seen is x equals x max times 1 minus e to the negative t over tau. And that's the one that rises up to its max and it settles in, reaches it in the limit. So this is time again, and this is whatever x is. Now x here is going to be some current or voltage. It's the current through an element, voltage across an element. But these are the only two possibilities that you have for RC circuits. So RC circuits, regardless of how you build them, the voltages or the currents, depending on whichever you're after, is going to look like this. It's going to be one of these two possibilities. And that's really it. Those are the only two possibilities for the general form of the solution for either voltages or currents across anything. All right, so let's work a problem then. Let's say that I've got switch, resistor, capacitor, CR, switch is open but the switch is closed at t equals 0. The values here for the capacitor, let's say, is 15.8 microfarad, resistor 23.0 ohms. Now here's the question. As this thing begins to charge up, there's going to be a voltage across this and a voltage across the resistor. You saw that right back here. The voltage of the capacitor rises, the voltage of the resistor decays. But you see they cross at one point right here. The question is, what is T? At what time is the voltage across the capacitor and the voltage across the resistor equal to each other? So, in other words, when is V sub C equal V sub R? That's the question. All right, so these are both charging behaviors. So remember how the voltage across the capacitor, voltage across the resistor, and remember the equations are going to be one of these two forms? Well, you don't really have to go through the mathematics if you can figure this out. For example, what's going to happen to the current here over time? Well, as it charges up, the current is going to what? Is the current going to get bigger or is the current going to get smaller? Ask yourself that question. If you convince yourself that the current dies down because the capacitor is becoming more and more charged, so the capacitor, even though the battery is pushing current around, the capacitor is opposing that because it's building up charge on its plates. So what does that mean? That means that I is going to look like I max e to the negative t over tau. Okay, so you expect that. All right, now why is that important? That's important because the voltage across the resistor is going to be I times R. So what's the voltage across the resistor going to look like? Well, it's going to look like some maximum voltage times e to the negative t over tau. Okay, well, what's that maximum voltage going to be for the resistor? It's going to be this. So the equation for the voltage across the resistor is going to be E times e to the negative t over tau, like that. All right, well, what about voltage across the capacitor? What's that equation going to look like? Well, as this thing starts charging up, it's getting greater and greater voltages across the plates. Now, the voltage across the capacitor is given by Q over C. So if you knew what the equation for Q looked like, you'd also know what the equation for voltage looks like. And you can very quickly figure that out, I think. The voltage across the capacitor is going to be E times 1 minus e to the negative t over tau. Now, if it takes you a while to figure that out, think it through. Maybe you need to start with Q first before you can derive voltage across the capacitor. But this is the form of the equation, general form of the equation for the voltage across the capacitor. This is the general form of the equation for the voltage across the resistor. The question is, at what time t are those two things equal to each other? So let's set them equal to equal to. I want this side equal that side, so, well, I'll just write it this way. E times 1 minus e to the negative t over tau is equal to E times e to the negative t over tau. There's the equation. Solve for t. And at that t value, that's when the voltages are equal to each other. All right, you'll see the e's cancel here. And I've got one, let's put this e over on that side is equal to 2 e to the negative t over tau. So e to the negative t over tau is equal to 1/2. Now we need to get rid of this exponential. Okay, how do you do that? Well, you take the natural log of both sides. So this becomes, when you take the natural log of the exponential, it's just going to be negative t over tau is equal to the natural log of 1/2. All right, let's get rid of the tau. We'll multiply by negative tau, and this becomes t equals negative tau times the natural log of 1/2. Okay, well, what's tau? We're talking about an RC circuit, so tau equals RC. So this is going to be minus RC natural log of 1/2. All right, now you're given an R value, you're given a C value, so this is going to be 23 ohms times 15.8 times 10 to the negative 6 farads. There's a negative sign there, can't forget that, times the natural log of 1/2. Okay, we need to do a computation. This turns out to be 2.39 times 10 to the negative 4 seconds, which is 0.239 milliseconds. So at time t of 0.239 milliseconds, after t equals 0, then the voltage across the capacitor is equal to the voltage across the resistor, like that. All right, now that we know that, the follow-up question, good follow-up question might be, what is the charge on the capacitor when the voltage across these two things are equal? When the voltage across the capacitor and resistor are equal, what's the charge on the capacitor? Well, in order to do that, you need to know the equation for charge on a capacitor. Let's do that in this region right here. Charge on the capacitor is going to be C times E times 1 minus e to the negative t over tau. All right, you know what tau is already. You know what C is. You know what E is. You know what T is. So take this value of T, plug it in there, and you'll get an answer out. I don't know what the answer is. I haven't done the calculation. But you'll get an answer out, and that's the charge on the capacitor when the two voltages across the two elements are equal. All right, another question might be is, what is the current at that time? Well, the current equation is E over R, e to the negative t over RC, or tau. Okay, you know what RC is, you know what E and R are. Take your t value here, plug it in there, and you'll get out an answer. That's the value of the current when these voltages across these two elements are equal to each other. Let's do one more, it'll be real easy. Let's say I have a capacitor, resistor. Let's put a switch in the circuit here. Let's say there's capacitor, resistor, and let's say there's an initial voltage across this of V0. Switch is closed at t equals 0. V0 equals 12 volts. Let's say R equals 1 meg ohm, C equals 1 microfarad. The question is now, how long before this, and at t equals 0, current begins to flow I. The question is, how long before I equals 0? So how long before I is 0? In other words, how long before I dies? It finishes doing whatever it's going to do. The answer is 5 tau, which is 5 RC, which is 5. R is 1 times 10 to the 6 ohms multiplied by C, 1 times 10 to the negative 6 farads. So how long is that? 5 seconds. That's how long it takes the current to die. 5 seconds. Okay, that one was real easy. You could probably come up with some of your questions on your own. Let's say the switch is closed. What is the current at 200 milliseconds? Well, you need to know what the current equation is going to look like. Is the current rising or is the current decaying? You can figure out that I is equal to I max times e to the negative t over tau. If you can get that far, then you need to figure out what's the maximum I. The maximum I is going to be e over r. Because when the switch is closed, that current instantaneously goes through here, so that's just I is equal to V over R. Oh, by the way, this E, the way I've got it drawn there, using the notation here, should be V naught. Okay, so that's a V naught. Let's write it over here. V naught over R, E to the negative T over RC. So that's what I is as a function of time. Now, take at t equals 200 milliseconds, plug it in there for t, and you'll get out a value that will be the answer. Okay, well, that's probably enough problems for RC circuits. Let's stop here. This finishes up our discussion of circuits, and we'll begin a new topic next time.